We live in an era where AI can write complex code, pass the bar exam, and literally generate photorealistic images out of thin air. It's incredible. But what if I told you these exact same cutting-edge systems consistently fail at a task a toddler can master? It's true. There's this fundamental disconnect with the physical world that's gone largely unnoticed until now. In this explainer, we're digging into a groundbreaking study that exposes a massive, almost unbelievable blind spot in modern vision language models.
Okay, let's dive into this. This central mystery we're looking at is deceptively simple. Can an advanced AI actually reliably distinguish right from left, or say, on from under? You'd think the answer is a resounding yes, right? I mean, these models are powering the next generation of visual search and robotics, but as you'll see, the research tells a totally different story. It turns out that when an AI looks at an image, its understanding of physical space, the basic spatial reasoning you need to navigate reality, is, well, fundamentally broken. Section 1. The AI Spatial Blind Spot. Historically, visual benchmarks kind of conflated spatial reasoning with basic object recognition. If an AI answered a complex question about an image, we just assumed it understood space. But maybe it just got lucky recognizing the objects. And this brilliantly illustrates what I mean. Take a look. On the left, we've got a dog clearly standing on top of a table. On the right, the exact same dog sitting under the exact same table. For us, the difference is instant, undeniable. But for a vision language model, this is an absolute nightmare. The AI sees dog and it sees table. It knows both objects are there, but the structural relationship between them, the actual spatial reality, just gets completely lost in translation. Section 2. The What's Up Benchmark Test.
So, to truly quantify this failure, researchers had to get creative. They created 3 tightly controlled evaluation datasets. They couldn't just rely on existing datasets because those are full of messy, real-world clutter. Instead, they've filtered 2 popular datasets, COCO and GQA, specifically isolating questions that only required spatial reasoning about 1 or 2 objects. But the real game changer is that first row right there, the What's Up benchmark. They manually took hundreds of photos of household objects in various positions with extreme control over lighting, background, the whole shebang. They strictly isolated the preposition. No distracting background clutter, just raw spatial relationships. Now, what's really interesting about this slide is how this approach completely removes what researchers call ambiguous biases. Think about it. The internet is flooded with pictures of mugs resting on tables. You're almost never going to see a picture of a mug floating under a table, right? If you don't control for that, an AI can just guess on and be statistically right without ever actually comprehending the image. So by taking their own photos and giving the AI options like a mug on a table versus a mug to the right of a table, the What's Up benchmark forces the model to actually compute physical space. No guessing allowed. But before dropping the hammer on spatial reasoning, the researchers ran a brilliant control test. They basically asked, wait, is it just that these models can't understand relationships between words and images at all? So they tested attributes, specifically colors. And guess what? When tested on linear analogies for color, like changing a red mug to a blue mug, the AI models performed really well. They hit around a 61% accuracy rate for complex analogies and a perfect 100% when directly evaluated. So the models absolutely understand attributes. They just have literally no clue about physical space.
Section 3. Startling Results and Failures. All right, so the trap was set. The researchers took their pristine, bias-free spatial benchmarks, and they evaluated 18 major vision language models. And the results are, well, they're startling. Let's translate this data into plain English, because this is absolutely the big insight of the paper. When human beings took these tests, we scored a near-perfect 99% accuracy. There's zero ambiguity to us whether a dog is left or right of a bench. But the absolute best-performing AI model, it scored 56%. Think about that for a second. Given multiple choice questions, the most advanced, highly trained vision models on Earth are barely performing better than a random coin flip. They are literally just guessing. Now, you might be wondering, is this just because they tested older or maybe smaller models? Actually, no. Not at all. The researchers tested models with entirely different architectures, from basic clip to advanced one-stack architectures like XVLM and BLIP2. They tested models with varying parameter sizes, going all the way up to 129 million parameters.
And what they found was that simply scaling up the model size, or even changing the training objectives, fundamentally did not fix the problem. This spatial blind spot is baked right into the DNA of how these models learn. Section 4. Investigating the root cause. So if architecture and size aren't the problem, what is? Well, the researchers dug straight into Layon 2B. That's the massive internet-scraped dataset that teaches these models how to see the world. And they uncovered 3 critical flaws. First, spatial prepositions are incredibly rare. They show up in less than 0.2% of the captions. I mean, people just don't write "a dog to the left of a tree" on the internet. They just write "a cute dog." Second, when prepositions are used, they're highly ambiguous depending on the camera angle. And third, learning prepositions is actually totally unnecessary for the models to succeed at their main training objective. Let me explain that last one because it's absolutely vital. Let's break this down. The AI is trained using something called contrastive learning. Imagine you're trying to spot a very unique face in a giant crowd of 30,000 people. You don't need to notice every tiny detail of their spatial environment to find them, right? You just need to spot their general features. Well, the AI is doing the exact same thing. In a massive batch of images, finding the Bernese mountain dog is pretty easy based on global visual features. The AI never actually has to learn the difference between dog on table and dog under table to pass its training test, because identical twins wearing different hats almost never show up in the same training batch. And honestly, when spatial text is actually in the data, it's a complete mess. Just look at this real image and caption from the Layon dataset. The caption says, "fabric with sewing item directly above and copy space." Okay, directly above what? The frame of reference is totally unclear. Is it from the viewer's perspective, the object's perspective? Because real-world training data is this messy, words like above or left become entirely dependent on perspective. It basically makes it impossible for the AI to learn a definitive mathematical rule for physical space. Section 5. Failed fixes and interventions. Now, like any great scientist, the researchers didn't just stop at pointing out the root cause. They actively attempted to patch the AI's blind spot. They tested 3 specific interventions. First, they tried renormalizing text priors. That's basically adjusting the math to stop the AI from guessing based purely on statistics. Second, they swapped out rare spatial words for more common phrases. And third, they tried fine-tuning. This is a process where you force-feed the model a highly concentrated diet of specific data, in this case, hard negative spatial captions, to literally force it to learn the difference. Their second intervention was super fascinating. When they evaluated models using the word behind, the AI failed miserably. But when they swapped the word behind for "in the background," which is a phrase that appears 4 times more frequently in the training data, there was this significant jump in performance. But here's the catch. This was just a rare statistical exception. It definitely doesn't mean the AI suddenly understood 3D space. It just recognized a highly frequent phrase pattern. It was a statistical trick, not a sign of true generalizable spatial comprehension. So the crucial point is what happened when they tried that final fix, force-feeding the model hard negatives. They literally created data that swapped left for right and forced the AI to tell the difference. And what happened? The models completely broke down. The fine-tuning loss, which is basically a measure of how confused the AI is, exploded to 5.0, compared to a normal level of about 0.01. So the models could narrow the options down, sure, but their underlying architecture simply couldn't process the nuance needed to consistently learn which spatial relationship was actually correct. Section 6. Future of vision models. We've seen the blind spot, we know exactly why it exists, and we know those quick fixes just don't work. Let's quickly summarize our journey here. Today's AI has a fundamental spatial blind spot, and it was brilliantly exposed by the tightly controlled WhatsApp benchmark. We learned that the internet-scraped data we use to train these models seriously lacks the necessity and clarity for spatial learning. We saw that you can't just slap a fine-tuning band-aid on it either because the loss just explodes. Ultimately, if we want AI to power robotics, self-driving cars, or advanced visual search in the real world, future models are going to require entirely new architectural approaches and way more intentional training data. Which leaves us with this final, provocative thought to ponder. As we rush to build bigger and faster neural networks, how do we build an AI that doesn't just mimic language, but truly, structurally understands the physical reality we actually live in? It is the next great frontier for machine learning, and clearly, we've got a lot of work to do. Thanks for joining me for this explainer today. Keep exploring, and I'll see you next time.